Hello and welcome to the YouTube channel of AI with Vic. And in this episode of Learning Numpy, we will try and understand slicing and cropping. Basically, we will try and understand like how we can select sub images from Numpy using Numpy slice syntax. We will try and understand flipping and downsampling. We will try and see like how we can horizontal flip and vertical flips and do stride based resizing. The other important part we will try and understand is boolean masking. Basically, the boolean masking will be used to demonstrate that how we can bright and dark regions in images. uh, we will also observe like fancy indexing like channel manipulation. We will try and reorder like select channels like instead of a red green blue blue green and red. And lastly we will try and do SVD compression. Like basically the idea is that SVD stands for singular value decomposition, and it's a technique used for dimensionality reduction. uh, so we will try and observe that how we can use the SVD compression for compressing or denoising an image using a component K. We'll go and understand in details there. Um, for that, like we will use our old image, like the cute dog image. We will first load that image, right? And let's start. So before for understanding slicing and cropping, let's understand one index or one syntax pretty deeply. So this syntax, like you can see here, like as I have already demonstrated in the first episode, that our image is basically an array, right? A NumPy array. If you see image.save, we have 225 rows, 300 columns, and three channels. Three channels means red, green, and blue, right? So this particular syntax is used throughout our NumPy episodes to understand that how we can select a particular part of a NumPy array. So let's say, for example, this states that row start, row end, row step, column start, column end, column step. What does this mean? Let's say, for example, if I want to select a particular area of NumPy, let's say example, here we are trying to select crop is equal to image 50 to 300, right? And I am not selecting any kind of row step. I am keeping it as one right here, and then 100 to, let's say, for example, 200, right? Let's see, you can see the cropped image here, right? So this basically syntax will be used in other steps also to demonstrate like flipping, downsampling, or even boolean masking. Okay. So the other part we want to discuss is flipping and downsampling. What is flipping? Flipping, basically we will try to flip the image using horizontal flip and vertical flip, and downsample also the image using strides. So when we say strides, what do we mean by this? This is stride. This is basically stride that we are saying. Like like a stride means that between this row start to this row end, you will take this stride. Like let's say, for example, if I say between 50 to 300, if I say here 2, that means that between 50 to 300 every second row is taken, right? So if you do this, what does it end up like? Yeah. So that's what the meaning of stride is. So let's try out the horizontal flip first. Okay. So let's declare flip h is equal to image, and then we will say all, and then columns and -1, right? And again flip v, and let's say, for example, downsampling we are declaring as two strides here, right? Two strides might not give a clear indication of how we have downsampled it, so let's give it a, so you can see here a horizontal flip and a vertical flip, and we have downsampled it. When you downsample, obviously you are skipping a lot of pixels there, so that's why the image quality goes down, right? Now let's go to the other part, which is basically boolean masking. We will try to brighten the dark regions here, right? The idea is that we'll first normalize the image f is equal to image dot as type float 32, and then np dot float 32, sorry, this should be np dot float 32, and then we will image f is equal to basically normalize it between 0 to 1. If you remember from the last class, if that normalization between 0 to 1 means that we are keeping each of the elements that are in the array in the range of 0 to 1, right? And then we use luminance. What is luminance here? So let's talk about luminance for a bit. So basically, as humans, like our eyes are basically susceptible to mostly green color. Like if you take the three major colors, like mostly like the grayscale images that are composed of red, green, blue, then green, and then red, and then blue. That's the reflection of the human sensitivity. So there's a common structure also, like a common recommendation of Rex 601, and we will use that particular equation to give the luminance. So let's say this will be luminance luma is equal to 0.299 star image f, and that will be basically uh, red region. Then this will be 0.587 star image f, and that will be basically red green. You can see here we are giving a higher weightage to green here, and then 0.114 star uh, image f comma 1. Sorry, this is going to be 0 1 2, the third axis 0 1 and 2, right? Then we will try and brighten a basically a wider set of dark pixels, right? So we can do declare a mask here that luma is less than 0.45, right? uh, Basically we are trying to target darker regions, like a higher threshold for a like a clear effect that we can show. And then we will introduce a bright here image f dot copy, right? And then bright mask is equal to, sorry, mask is equal to np dot clip uh, bright mask uh, star 0.5, and this should be kept between 0 to 1, right? So let's see this now. Okay, yeah, this is wrong. So yeah, you can see the brightened darker regions, like you can see here the darker regions that we have a brightened part here, right? So that is how luminance can be used to basically masking, boolean masking can be used, and with the combination of luminance to basically brighten the darker regions, right? Okay, now the other part that we would like to discuss today is basically channel manipulation. A channel manipulation, basically what I mean to say that we will try to place reverse, like kind of a red green blue to blue green and red. Let's see that. Like, so we'll declare bgr is equal to image, and then this, and then this, and 2 comma 1 comma 0 here, and then plt dot im show bgr, right? And this will be bgr swapped, you can say swapped, and then plt dot show, right? And probably I will try and show the red channel only to be highlighted. Let's say image dot copy, and this is only red, and let's see, does this work? You can see that only the red channel is being highlighted here. Here we have swapped the BGR, like the red, green, blue is into blue, green and red. Now, why am I discussing all these techniques here? You need to understand that while when you are training, let's say for example, let's take for example, you are training a machine learning model to classify between dogs and cats, right? And when you have trained a model, now you receive some images which are like this type, which might be also this type, and your model is not able to recognize that, right? So these kind of image augmentations, remember the term augmentations, image augmentations. There are a lot of techniques in image augmentation, we will discuss that, but this is a starting point to understand that so if you perform image augmentations on your data set, you will create a lot of other training examples, kind of a robust training examples, which you can feed into your machine learning model and make it much more robust for predicting. Okay. The last part which we want to discuss today is SVD compression. So let's understand SVD compression in a very like a 5-year-old child, right? So let's say for example, you are creating a wall, right? A wall, right? And in the wall, you recognize that only 20 or 30 bricks are important to hold a wall and give the shape to the wall. Although the quality of the wall will be low, but still you require lower bricks there. That's what SVD compression does. SVD compression stands for singular value decomposition, right? It's I'm showing here for images, but you can apply it for dimensionality reduction also. That's a different part. We will discuss that, right? And using SVD for images, we can very well approximate it by basically a low rank matrix. If you do not remember low rank matrix or a rank, what is a rank in a matrix, I will attach a description link where I have discussed in details about what is a rank in a matrix and how we can calculate that. Okay. Okay, so let's go into that. We will first read the image here again, plt.im read, and that is cute dog dot jpg, right? And we will normalize it image by 255.0, basically keeping the values between 0 to 1, and gray is equal to image dot mean axis is equal to 2. Ah, my bad. And then we have here USVT. So basically what is USVT? We are basically decomposing the image matrix or the image array into these three matrices, which is np dot lin alg, right, dot svd, and you have gray here, right? Now I choose k is equal to 10, like basically k is equal to 10. Let's see the effect of k is equal to 10 first. K is equal to 10. Basically I'm saying that okay, only these components, only these many components are important to show my image here. So let's say I have taken this here uk, and then np dot diagonal. Let's see if it can work or not. You can see only with 10 components, we are saying that only 10 components are necessary to show the image, like the image can hold up. Obviously it has been compressed, but the quality has gone down. What if I move it to 20? The quality goes up, right? But it's not that much of compressed now. If you go to 30, you can see here now it's a bit much more clearer, and with 30 components, and obviously it's not less, it's a lot less now compressed. Okay, so this is what I wanted to discuss with you guys in this episode, where we have discussed and talked about these five types of like operations you can learn in NumPy. If you have any questions or any comments, please mention it, And if you like this video, please like and subscribe. Thank you.